I think I said on the first day of this conference that I'm only here because I'm interested in integrals, in numbers, and very specifically those that come from Feynman diagrams. And about 30 years ago, I had an idea that multiple zeta values would result from Feynman diagrams, and that was confirmed. 20 years ago, Dirk Kreimer and I decided to get tough with these multiple zeta values and try and conjecture how many of them there are. And there's been some interest in that subsequently. And about 10 years ago, I worked with Johannes Blumlein and Jos Vermasseren to provide people with the multiple zeta data mine, because that idea from 30 years ago had now become an industry. So I want to say nothing about multiple polylogarithms, because that's very old stuff, and it's been magnificently addressed yesterday by Jean Egal. So I want to move on to the numbers that occur after that, and you might expect me to talk about elliptic integrals. But in fact, there's going to be something more interesting than elliptic integrals, either integrals of elliptic integrals or squares of elliptic integrals. But I've also magnificently set up on the simple elliptic integrals that we first encounter beyond polylogarithms by Gerald Dunn's talk. So here's my plan. I want to start with a physical example, the most physical example I can think of. So if you're worried by physics, shut your eyes, close your ears for the first 5 minutes, but then everything will be safe. And then I want to talk about automorphic forms, which if you're a mathematician, you should know more about than me. And then I want to say that there are, in the past few months, David Roberts and I have discovered quadratic relations between Feynman diagrams, encoded by Betti and Rham matrices. If you haven't heard of those, I will make those very concrete. And we've found these up to all loops. Now, a loop is just the number of momenta running round a Feynman diagram. So let me draw a Feynman diagram. How many loops am I going to give it? Let me give it 1, 2, 3, 4, 3-loop Feynman diagram. And it's got some masses of the particles that are propagating inside. And I'm interested in simple numbers, so I'll put all those masses equal to unity. And it's got some energy coming in down here, W. And I'll put W equals 1. And this is, the number theory of this is directly relevant to the magnetic moment of the electron. But then I want to be considering such Feynman diagrams as periods. They are periods in the sense of Zagier and Kontsevich. And there are remarkable relationships between them that probably indicate deep underlying algebraic geometry and something that generalizes automorphic forms. But I'm going to go far beyond the places that algebraic geometries can come up with concrete results. I'm going to go up to 22 loops. So what are the types of numbers that I'll be getting? Well, they're the things on which algebraic geometers and people interested in automorphic forms converge. L-series. A zeta value is an L-series. The Birch-Swinnerton-Dyer conjecture is concerned with L-series at the center of the critical strips of modular forms of weight 2. So these are the numbers which I shall be offering to you as a gift from quantum field theory to mathematics, and they'll be related conjecturally by deep ideas from Pierre de Ligne by rational numbers. Like 691 relates zeta of 12 and pi to the 12. But thanks to Feynman, and a lot of help from my collaborator David Roberts, we've been able to find empirically these numbers for motivic weights far greater than otherwise investigated. Okay, that's the preamble. So now the physics, which has 5 chapters very quickly. It's like the Christian and the Jewish Bible. It begins with Genesis. In 1928, Dirac announced exactly the magnetic moment of the electron in units called the Bohr magneton. He said, look at my equation. It shows that the magnetic moment of the electron is exactly equal to 1. And he got the Nobel Prize for that because the previous answer was a half. So showing that previous ideas have been wrong by a factor of 2. If you ever hear about the G factor of the electron is the ratio of Dirac's new value to the Bohr's old value. And then we have to go to 1947 before we have an exodus from the certainties of relativistic quantum mechanics to the deep problems of relativistic quantum field theory, besieged by infinities that Dirac refused to accept. Dirac never really believed in quantum field theory because he said, I'm an engineer. Dirac was educated as an engineer at Bristol, and engineers don't believe in infinity. And he said that to me personally in 1981. So Julian Schwinger got the Nobel Prize for saying that, oh, that was interesting. How do I go back? Go forwards, but is it? Ah, yes, that's right. If all else fails, use your fingers. So he said, no, he said, Dirac's wrong, but by a very small amount, by 1 part in 1,000. He said quantum field theory means that this 1 is actually an expansion, presumably, we don't know whether an asymptotic expansion or a convergent expansion, now I have to press this button. Yeah, there we go. In the fine structure constant, which is approximately equal to 1 over 137. So divide 137 by pi. Oh. Divide 137 by pi. Why can't? Yes. Divide 137 by pi and then take a half of it. So that's about 1 part in 1,000. And then he got a Nobel Prize for that. But the subsequent calculations were kind of clear. We had from the Feynman rules and the ways from Freeman-Dyson of renormalizing quantum field theory. And in 1957, we have the 3rd chapter. There had been a previously incorrect value. And we start to see here zeta values. Unfortunately, I can't point at them. But can you see zeta of 3? And also pi squared times log 2. Well, that's log 2, as we heard from Jean, is a decorated zeta value. So we see a rational term, weight 2, and weight 3, and there's a term in weight 3 which has depth 2, pi squared times log 2. Now, these are very difficult calculations, and in 1996, LaPorta and Rham finally managed to achieve an analytic result for the what we call the for what we call the 3-loop corrections, and one of the topologies would be like that, but it would have various photons interacting. And a new number appeared, interestingly, and I have predicted this number in advance. I said, yes, of course, you will see all the numbers you saw before, at weights 2 and weight 3, and at weight 5, I expect you to see zeta 5 and zeta 3 times zeta 2, and they said, sure, we've got that from our diagrams already, but what's the other number? And I said, well, it will be the only irreducible, decorated, multi-zeta value of weight 3 and depth 1. And can you see there? Well, unfortunately, I cannot point, so it's an impoverished talk. A stick! Oh, fantastic. Right, great. Right, so can you see here that it's decorated by the second root of unity. It's an alternating sum. If I had a positive sign down there, it would be zeta 3, 1, which is a multiple of pi to the 4th. So we get pi to the 4th. So this is very interesting. You see, these numbers are appearing in physics context, the simplest and the most basic question we can ask. That's a number. So the 5th chapter of the Pentateuch is the most puzzling one. It's called Deuteronomy. It was discovered rather late, and it's the second book of the law, because things start to change in the Bible, in Deuteronomy. So early this year, after 10 years of isolated, dedicated work, Stefano LaPorta obtained not quite yet an analytic result for the Forloop corrections, merely 4,800 digits. Seems very temperamental. merely 4,800 digits. So when it disappears, all shout at me. Yes? 4,800 digits of it. And it's split here. I'm not tall enough to show you. I'm struggling. Really, a teacher without tools is quite difficult, finds it quite difficult. Can you see it's got 4 terms? The first one, P, contains polylogarithms. Polylogarithms decorated with roots of unity. The first, the second, the third, the fourth, and the 6th root of unity. Just like Eric Pantzer had found the 6th root of unity in massless Feynman diagrams. And they go up to weight 7. Well, those were what expected, but we know something new has to happen here. So the new thing I want you to concentrate on is called B. It's a Bessel moment. I shall explain how and why. And then after that, there are things even more refined. So E, it has a weight 4. Now, how do I assign a weight to a Bessel moment? Well, you will see later. But if it were a polylogarithm, which it is not, it would have weight 4. It has, in a well-defined sense, weight 4 going beyond polylogarithms. And there are other things that are not polylogarithms, that are integrals of logarithms times products of elliptic integrals. And these have well-defined weights, 5, 6, and 7. And then there are these difficult people. U. U, can you see up there? Which means that unknown, undetermined, at present only known to 4,800 digits, but under intensive investigation. So what am I going to do? I'm going to look at the first place that numbers beyond polylogarithms occur, and I'm going to look at the simplest place. If you like, I'm doing what Einstein said you should never do. Einstein said, I have no patience, he said, for people who take a plank of wood, anyone know this quotation, and look for where it's thinnest and drill a large number of holes. Yes? Well, that's exactly what I'm going to do. The plank which I address is the number content of quantum field theory beyond polylogarithms. I take it from physics. I look where it's thinnest, the simplest example of it, and then I try to see the underlying mathematics, take it away from the context of quantum field theory in a form that not only you could understand, but Euler and Gauss could understand, and then drill a large number of holes, and that means going to as many loops as possible. 22 loops. I was up to, in December of last year, I was up to 6 loops, and now we're up to 22 loops. So, what is this Bessel moment? Well, this particular number has amazing rational numbers down here. This just means they've calculated thousands of Feynman diagrams and added them together. But as far as all you need to know is this is a rational function of t, which is integrated from 0 to infinity, and it contains only t and t cubed, odd powers of t. And in here, we have Bessel functions, right? There are the equation that they satisfy was written down by who? Who do you think wrote down Bessel's equation? I'll give you a clue. It was a Bernoulli. Does anyone know which Bernoulli? That gives you about 10 choices. Ines? Where's Ines? Your beautiful son that you were talking to this morning, what is his name? Daniel. Okay, Bessel's equation was written down by Daniel Bernoulli. How many people here came by aeroplane? Stick up your hand if you came by aeroplane. Okay. How did Daniel Bernoulli get you here? He is the parent of hydrodynamics, yes? And he said that when air flows fast, its pressure decreases. And he gave an equation for that. That's what kept your aeroplane up in the air. The aerofoil was designed that airplanes can only fly through air, they can't fly through space. The air on the top of the aerofoil wing is going faster than the air underneath. Okay? And the principle of lift and the principle of flight. Now, if you think about that aerofoil wing, something very, very funny happens, right? Because you've got fast air and slow air coming down here, and they meet, and then something beyond Daniel Bernoulli's competence, turbulence happens, yes? But do we know the name of the first person to describe the onset of turbulence and to quantify it? He has a number named after him, which is a criterion for turbulence. His name is Stokes. Anyone remember him appearing? So what I want to say is that these physicists, these mathematicians that physicists that are admired by other mathematicians, Bernoulli and Stokes, were interested in very concrete physical situations as well as abstract mathematics. So, thank you. Thank you very much. So here I have 5 Bessel functions, so I better draw another line here. And it comes from a Feynman diagram, with 5 massive particles in the intermediate state, so I have to put in some photons down here, and one of these electrons going backwards in time interacts with a magnet. And it's coming in. It has W equals 1 because it's a physical electron. The mass of the electrons equal to 1 in my units, and all of these intermediate states. So if we have tricks of getting rid of, to find the number theory, getting rid of the massless photon lines, I get down to this. So inside this integral, all you need to know is I'm giving you the Feynman rules not in momentum space, not in Schwinger space, not by the Kutkowski rules, but in coordinate space. And there's an integral from one point in space-time to another point in space-time. I give it back to the chairperson. I do feel very poorly served at present by the technical facilities. Back to the stick. This Bessel function is a solution to Daniel Bernoulli's equation for the 0th order Bessel function that has a logarithmic singularity at the origin, but falls off exponentially at large t. T will stand for time in here. It's the proper time between here and here. And there are 5 of them. Now, that exponential fall-off of the Bessel function is the origin of another Nobel Prize from Yukawa, who sought to explain the short range of nuclear forces by the exponential fall-off of a force law involving the propagation of a massive particle. And that massive particle was subsequently discovered, and it's called the pion. It was discovered in the week of my birth. I had to go to a conference in Bristol to work out who was older, me or the pion, and it turns out that I'm older than the pion by 2 days. Now, what's this I naught? Well, this I naught is associated with the external momentum coming in, and it's the sibling of K naught. It satisfies exactly the same differential equation from Daniel Bernoulli, subsequently claimed by Bessel, but it's well behaved at the origin. It has a perfectly convergent expansion in powers of t squared with infinite circle of convergence. But of course, the price it pays for being well behaved at the origin is that it blows up exponentially at large t. But that's okay because I've got 5 of these things. So this is a very easy integral to evaluate. It's by far the most convenient way for these types of integrals. And here's the value of the contribution that was found. Okay. So now that's all I want to say. And I want to jump straight to automorphic forms. How do automorphic forms get in? Well, they get in because, as I said, there are numerous ways of writing Feynman diagrams. So let me look at this Bessel moment. There it is at the top. M, A, B, C. And it just consists of A powers of I naught, B powers of K naught, and C powers of T. So immediately I've generalized, right? And you forget about quantum field theory. This will be the subject, the mathematical object on the side of the integrals. I've told you that I can present it in many ways. I give you the way that algebraic geometers know. So let me look at a particular example, isn't it? You know. Down here. So let me take an example in which A is equal to 1. I don't think they want me to give this talk. A is equal to 1, B is equal to L plus 1, so it means I have L plus 1 particles propagating in the intermediate state, so it's an L-loop diagram. The first Betti number of this diagram is equal to 4. And we can represent it as a projective integral, but I've made it into a perfectly ordinary integral by an integral over L plus 1 parameters with one of them set equal to unity. Do I get extra time for this, Madam Chairman? Aha. Thank you. It really is very, very difficult to talk about mathematics if you can't point. Okay. So, these are the internal Bessel functions. That's, I only have one external one down there. Let's look at that situation. L-loop diagram. It's an L-dimensional integral over, can you see, d log x. 1, d log x2. And at the bottom, we take the sums, and that was my fault. We take the sums of the x's, and we multiply them by the sums of the reciprocals of the x's, and we subtract 1. That's for the external momentum. Now, people are likely to ask me in the questions, what's the Picard-Fuchs theory of this? And the answer is, can't tell you. Because for that, I would need a parameter with respect to which to differentiate. So if I had some w squared coming in here, then you could ask me, what's the differential equation satisfied by that? And you'd find out when you go up that you have a Calabi-Yau manifold or a K3 surface or something. You know, these are the simple examples that we're talking about, and later on you'd puzzle over it. But I say I'm going to a number, not a function. So I'm looking at, if you like, a variety where I've gone to a very, very special point. And then mathematicians think very hard about that. They blow up the singularities, and they say, maybe it's a number of the following type. Now, that's just one of those integrals. Here I want to look at this matrix, which unfortunately has got cut off. That's probably my fault, but we can do something about that. The matrix down there. But you might say, well, what happens? How do I get? This is 1 power of t down here. So it's integral t dt. T cubed dt, I just differentiate with respect to the external momentum and then put it equal to unity. How would I increase the number of powers of I naught? Well, instead of, if I was a momentum space, the propagator of this will be 1 over p squared minus m squared. I put it on its mass shell and have delta of p squared minus m squared. So I've just written this one down here because this is what's called the general sunrise integral. It generalizes what I call sunrise and what less optimistic people call sunset. You're supposed to see the horizon there and half of the sun, the horizon. So these generalized sunrise diagrams. And 10 years ago, I looked at the five Bessel problems. So 1, 2, 3, 4, this one, right? And empirically discovered that there was only one new constant down there. And I've written the matrix of the 4 things I evaluated in terms of this constant. And empirically, the matrix involves the reciprocal. Now, I hope this rings some bells with what Gerald Dunn was talking about when he was talking about elliptic integrals, and when I asked him about the Legendre's relation. So there are 4 integrals down here. They involve one new constant, a beautiful constant. I'll tell you what it is. Can anyone tell me quickly whether the matrix, whether the determinant of that matrix involves this new constant? Should we have a vote? The determinant of this matrix, well, I tell my students that you can take out pi squareds, doesn't change the determinant, and you can take out 2 15 squareds, and you can take out that. So really the determinant is c times 13c plus 1/10 c minus c times 13c minus 1/10 c, which I compute to be equal to 1/5. Yes? So this number, right, this new number that comes in, so what is it? Is it one of Gerald's wonderful, beautiful elliptic integrals? No, it's more beautiful. It's the square of one of Gerald's integrals. And do you remember he said elliptic integrals are given themselves by the square of theta series? He wrote down theta series. So this is the 4th power of a theta series, but a theta series at a special point. He had theta of q, which was equal to exponential 2 pi I tau, and tau was some physical parameter in the theory. I've got numbers. So I must be at some very special point. Special point down here, you can see that tau is equal to the square root of minus 15. Down here, I've got the square of the complete elliptic integral of the first kind evaluated at the 15th singular value. So a beautiful number. Okay, but we know that modular forms tend to be associated with elliptic curves. Now, the modular form that I will have has to be deeper and more beautiful than the ones that Gerald had. His were related to the Schwinnerton and Dyer conjecture, where you only have weight 2. So, of course, mine will have bigger and better weights, and it's weight 3. It's a weight 3 modular form with level. I tend to use the word conductor, but 15. And here I define it in terms of Dedekind's eta product, which is a very simple thing. Now, this Q here is just a formal expansion parameter. Those of you who want me to go into the upper half of the complex plane and talk about cusps are going to be deeply disappointed because I've got numbers. So Q, I'm just going to treat as an expansion parameter. Dedekind says, take the products of 1 minus Q to the K over all K. Well, I define eta to be eta of Q to the N. And it also has this 1 over 24 down here, and it tells only when you've got that 1 over 24 have you got something called a modular form. So we better, but I want something that has a rational expansion in powers of Q. So here's the recipe. Take eta of Q cubed and eta of Q to the 5th and cube it, and then take eta of Q to the 1 times eta of Q to the 15 and cube that. Well, can you see, you can count on your fingers, 3 plus 5 is equal to 8, yeah? 8 times 3 is equal to 24. 24 kills that. So this is a sequence, this defines a sequence of integers, the coefficients of Q to the n, starting with a of 1 is equal to 1. So all I've got from this modular form for my physics problem is a set of integers. So what can I do with a set of integers? Well, one of the things you can do is use them, particularly if they have the normal multiplicative property, to define an L-series. So I take these Fourier coefficients of this modular form and say that they're the numerators of this L-series. The 5 just tells me it comes from the 5 Bessel problems. Of course, this is only defined when S has a suitably large real part, just like the Riemann zeta value. But if we can find the functional equation for it, we can analytically continue it and ask interesting questions, like what its value is in the case of a zeta value on the critical line where the Riemann zeros are, or in the case of Schwinnerton and Dyer at the center of the critical strip. Down here. So here's the functional equation for this. It has degree, it's for a modular form, it has degree 2. You have to multiply by 2 gamma functions. The conductor with a suitable power of pi. And when I define lambda to be this, then this has a property. So I define lambda to be that. This has the property, the functional equation here is that lambda of S is lambda of 3 minus S. So it tells me my critical strip runs from 0 to 3. And so what am I going to do? I'm going to look at an integer between 0 and 3. There are 2 of those, 1 and 2, and they're related by the functional equation. So there's only one number. There's only one number that I can get. And of course, it's a number in my Feynman diagram, otherwise I wouldn't be talking about it. And it's at the 15th singular value, and there's a beautiful theorem called the Chowler-Selberg theorem that says the elliptic integrals at the 15th, at any singular value are products of gamma values. And we saw an example of that yesterday in Inesh's talk, because from the quantum field theory that gives you a custom anomalous dimension, she had a Stokes parameter, remember the guy who described turbulence, which involved the square of gamma over quarter, which was the origin, and the evaluation of that as an elliptic integral was the origin of Gauss's discovery of the arithmetic geometric mean. So there's lots of mathematics in that. Right? Now, all of this is 10 years ago, but you haven't heard me talk much about it because you've invited me to talk about polylogarithms, which are now reasonably well understood. But last night, I read a paper posted by this wonderful person, Yong Zhao, sometimes at Beijing, sometimes at Princeton, who sent a proof of all of the entries of that matrix. It took John Baldwin and I hundreds of hours to prove this, almost as long to prove that. It took Spencer Bloch, Matt Kerr, and Pierre Van Hove about 5 years from me first doing it to prove this. And this week he proved that, and so my value for the determinant of the matrix is now proven. And the determinant is rather interesting. You know, I asked Gerald what his determinants or discriminants were, or Vronskians, or whatever you like to call them, constants. And mine's an algebraic number times pi cubed, but it involves 3 to the 3 and 5 to the 5. I'm going to go on to a higher number of loops where I find similar interesting determinants that involves the square root of 31 to the power 31 times the square root of 29 to the 29 and all of the primes down there. So very, very rich structure just of these treating pi as given in these algebraic numbers. But I want to think much more of this, that the Feynman diagrams evaluate. So now to go on, now I can now go to the LaPorta problem with 1, 2, 3, 4, 5 Bessel functions in the intermediate state. And here, you can write down some expression for what the L-series are if you know about hypergeometric motives. It's not these that I want. I already know what the integrals are equal. What I want to know is how are the critical values of the L-series, of this case the modular form associated with the algebraic variety of the physics problem, rationally related to Feynman integrals. So here they are. There are 4 Feynman integrals that I've written down here. They all involve 6 Bessel functions. And here you see the concept of weight works out beautifully. This is a sunrise diagram that I says has weight 4. Well, it's equal to pi squared times an L-series evaluated at 2. So if that L-series was just the zeta function, you say it has weight 4. Now here I cut one line, so I have a 3-dimensional integral over Schwinger parameters, so I expect weight 3, and yes, I find in the critical strip the L-series evaluated at 3. And here I cut 2 lines, and here I see it evaluated at 2. So the concept of weight that we just think of, generalizing the powers of pi continues beyond the language of multiple zeta values. And this is extremely important when you're seeking empirical relationships, because you already know that what quantity to take, and you're just looking for a rational number. So these rational numbers are totally empirical. That's 3, and that's 3 down here, and that unity times pi squared. I promise are accurate to 10,000 decimal digits, but I don't know a single mathematician in the world who yet knows how to do those, given how long the previous ones for 5 Bessel functions. However, Yong Zhao may make progress on this. But this is old stuff, right? But I do this because this is the LaPorta frontier. At 7 loops, number of Bessel functions is n. If I talk about loops, then just subtract 2 from n. Feynman diagram people like to hear about loops. This is a 7 Bessel function problem. I needed some new mathematics. It gets difficult counting zeros of varieties in finite fields. So here's what we do. We go to mathematicians and say, what's the closest you can get to a Bessel function in a finite field f of q? Well, a Bessel function is something like the integral dx of x of t plus 1 upon t times x, or something like that. So they come up with a prescription in finite fields. Here we see finite field with characteristic p. Here we see a pth root of unity, because what I do is I take the primitive pth root of unity and I raise it to a power given by a trace of Frobenius in f of q over f of p, something that takes an element of f of q and turns it into an element of f of p. And I sum over all of the elements apart from 0 in the finite field, and I have a parameter here, a, which is like my time in the Bessel function, and so I define for every element of the finite field this k of a. And then what I want to do is to take moments of it. So what I need to do is to take powers of k and sum up over all the elements of the field, and they take symmetric powers. Here's a complicated construction down here, but you split up k into g and h whose products are equal to q. But if you work that out, you can translate this directly into sums over the finite field of powers of this Bessel function. So this is pretty close to a Bessel moment. These mathematicians didn't realize it would ever be used by someone doing quantum theory, but Philip Rober is the person who I attribute this to. Now, what do you do when you've got something in finite fields? Well, you try and work out the local factor of the L-series, if there is an L-series associated with it. That there is an L-series associated with it was not foreseen by many mathematicians. And to do that, you use this Lefschetz formula that says you evaluate this particular moment I've divided by q squared. Still gives me, these are integers down here. So now I take the sum over all k of c at p squared, c at p cubed. We've seen such formulas in this talk down here. And I exponentiate that infinite series, and it gives me a very simple polynomial. Now this is deep structure, deep motivic structure. I'm not supposed to use that word because I don't understand it, but mathematicians use it. So what it means really is that c of p and c of p squared, maybe if this polynomial only has degree 2, determine c of p cubed. Well, that's what happens in a modular form. If you tell me the Fourier coefficients at the primes and the conductor and the character, then I can find it at all powers of the primes. When you go beyond modular forms, you need more information, but a finite number of information will tell you what this infinite sum is, and this infinite sum is the logarithm of a polynomial. So what do you do when you've got these local factors? Well, you do what Euler did. You want to define an L-series, so you take a product over the primes. Now, this has parameter. This is the number of Bessel functions. This is the local place, the prime at which I'm looking. This is an abstract variable t that is the argument of this polynomial. And all I do is I put t is equal to p to the minus s, just like. So if this polynomial was the unit polynomial, then I'd have 1 over, was just t, then I would put t is equal to 1 minus t. Then I'd have Euler's formula. And I should be looking at such L series up to 7 Bessels, and then things start to get more complicated and more interesting. So having done that, then, and of course what I'm supposed to tell you is that there's a relationship between this beautiful mathematical object and the beautiful physical object that I started with. So here it is. Here's the 7 Bessel, 5 loop sunrise diagram cut once, and it's related. So it's something I would expect to have. If it's 5 loop cut once, I expect it to have generalized weight 4, and yes, it turns out to be pi squared times the L series associated with this Bessel function. So here's the concrete things for 7 Bessel functions. I'm just taking these. The local factors give a cubic. It would be quadratic if it was a modular form. There's a refined character, chronic of p of 105, that measures whether or not p is a square, modulo 3, 5, and 7. These are called the primes of bad reduction. They're the really interesting primes that mathematicians don't like them because they obey their own special and refined rules. And for the primes of good reduction that don't divide 105, we get that. Without guessing, very often mathematicians, when they construct L series, have to guess the local factors at the primes of bad reduction. Straight out of the Kloosterman moments, I find this. Then it's not a modular form. It comes from the symmetric square of a modular form of weight 3. These are the Hecke eigenvalues. So all of this beautiful structure is coming on already at 5 loops and beyond modular forms. They come back at 6 loops with 8 Bessel functions, and this will be relevant to the magnetic moment of the electron 1 loop further than we've managed to investigate it so far. And here, out of these eta products, I make a modular form of weight 6 and conductor 6. I have 8 Bessel functions. Here's a sunrise diagram, which is pi squared, which I expect to have weight 6, and it's pi squared times the SL function at 4, and then I cut lines and get it at 5, and at 4, and at 3. And also, down here, there's some extra sophistications. As I said, I have to modify the L function by taking out factors I've already seen with 4 Bessel functions, and there are infinite family of sum rules of this type, which I advertised as a very, very hard problem in honor of another of my colleagues, Richard Crandall, who died a few years ago. And that challenge of proving that those are integers was met by someone whose name I've already mentioned, Yong Zhao, 2 weeks ago, before I spoke in Paris. So I sent him an email saying I had to change my transparencies the night before I spoke in Paris to include one mention of one of your proofs. I had to change them last night in Marseille to include one of your proofs. My next talk is in Edinburgh in 2 weeks' time. Please stay in contact. Now, there are also diagrams called vacuum diagrams where you remove the external line and only have Bessel functions, and these are related to non-critical L-series, something that mathematicians find very, very surprising, that I can get outside the critical strip, but only when I have the modular form for 5, 6, and 8 Bessel functions. You see the strip here runs from 0 to 3, so I'm 1 unit outside. Or you could think of this as being the derivative at s equals -1. And here I have determinants, and they include vacuum diagrams. Now, I've only 20 minutes left, but that was really setting up the context. Pardon? +5, 25 minutes left. Wow. I get to give my joke then. I was worried that the technical problems were going to erase my joke. This is just a signpost for what comes later. I've really tried to show some of the ingredients, but the ingredients are the following, is that David Roberts and I, starting in Australia in January, managed to get beyond 8 Bessel functions, 6 loops, by taking local factors from cloostermal moments, sometimes with adjustments, guesses of the gamma factors, signs, and conductors in the functional equation. There can be a sign in that functional equation which gives you a 0 and central vanishing. And also, inside the big determinants we were taking, there were quadratic relations between Bessel moments. And there were also some rules when the number of Bessel functions was divisible by 4. And we found that we could go deeper into the connection between periods, integrals that come from Feynman diagrams, and L-series than anyone had gone before in comparable contexts. The comparable context of our hypergeometric motifs, of which Gerald gave you 4 examples in his 4 physics things yesterday, all of them at weight 2, associated with levels. Was it 2, 3, 4, and 6, Gerald? Yep. Thank you. Right, so now I want to do something that really mathematicians do all the time and is profoundly unhelpful. I want to give a series of definitions, completely unmotivated, and then state a conjecture that's utterly well defined given these definitions, yes? And then, if I'm a true mathematician, I should just shut down and say that's the end of it. So let me do that, but it's a very refined construction that I'm going to make before I make my conjecture. So here's a refined construction. You remember this Bessel function, I0? Well, actually, the context in which Daniel Bernoulli studied it was when we put the argument equal to I times t. This means that it oscillates. And then it's called J. And he proved that it had an infinite number of zeros, so mathematicians, not just interested in aeroplane wings, but numbers of zeros. It's an oscillating Bessel function. And J1 is just minus its derivative. So J0 squared starts off like unity, and if you work it out, twice J0 times J1 starts off like unity, and they both have expansions in powers of t squared with rational coefficients. So you could use them as generating functions for interesting rational numbers. And I'm going to do that, but I'm going to divide by C of t, and C of t is the unique combination of unity J0 squared and t J0 J1, which vanishes like t to the 4th. So I'm going to divide it by the right power of t to the 4th, and so out of this thing, here I've got this series, and I'm going to divide by this series and define v and w to be, right? So you're now in mathematical mode. You don't know why I'm doing this, right? But you know what I'm doing. Can you see defined to be? So I've defined a set of numbers. So what I'm going to use these rational numbers for is as constants in a recursive definition of an infinite family of bivariate polynomials. Don't ask me why, because I'm in mathematics mode. I'm not motivating what I'm doing. So now I define these polynomials recursively. I say I've got this h of 0 of y and z, and it's equal to unity. And here I write a recursion that looks a little bit like Hermite's recursion, so that's the reason I use the letter h. But it's got 2 variables associated with it. So the only place Z enters this polynomial is here, and then via all of the polynomials of lesser weight, or whatever we call them. But these constants that I define down here occur in the definition. So these are combinatoric objects, these are combinatoric objects. Right? So all combinatorics agree that I have a set of rational polynomials in two variables. What do I do with them? Well, I take particular combinations of them. And for the first time, I transform the arguments, normalizing it, and now I've got something, this n is going to be my number of Bessel functions. So I've now got a polynomial in n and in c, which I haven't told you what it is, it's just some, but c will be equal to an integer in my subsequent work, so this will be a rational thing, and then I have a family of S of these. So what do I do with these? And then this is the most remarkable thing. I define a matrix. I give it the letter D, because I'm going to associate it with the Rham. For each number of Bessel functions n, I define a Dn. The size of the matrix runs from about 1 to about n upon 2 to the ceiling of n upon 2 minus 1. And so A and B run up to this K. And then I have a finite sum over this C, runs from minus B to A. Quite unusual to have summation going from minus an integer when you're dealing with matrices. And a product of these polynomials in n, summed over C, times C to the power of n. So this is clearly a rational number, because these are rational polynomials evaluated for this number of Bessel functions. And I define that matrix. Okay, I call it a Rham matrix, but it's just defined down there. So this is a recursive construction of a combinatoric object. Now I define things that I call period matrices, and this is where the physics is. They're just these Bessel moments, but I turn them into matrices. And according as the number of Bessel functions is odd or even, and they have matrix elements, there's a matrix element, a label U, that's kind of associated with the power of T, and a label A that's associated with how many I naughts and K naughts I've got down there. And now, again, completely unmotivated, I define this matrix, which I call a Betti matrix, by taking the rational de Rham matrix, as so defined, and multiplying on the left by this period matrix of transcendental numbers, courtesy of Richard Feynman, and on the right by its transpose. Okay, so I've now defined exactly what I'm doing. You could go off and read that. And now I make the following conjecture. These Betti matrices are rational. So I've taken here these amazing numbers from Feynman diagrams. I've taken a quadratic, something that's bilinear in them, just like in the Birchman and Dyer conjecture, just like in Legendre's relation, with these integers doing down here, and I assert that the results are integers. For all number of loops and for all elements of these matrices, and I give a concrete formula for the conjecture, and I say that these integers come from two people whom Jean mentioned yesterday, strictly in the context of multiple zeta values. I asked him after his talk, I know that you put pill and pal into the multiple zeta value problem because the Bernoulli numbers occur multiplying even powers of pi and zeta values, but here are the Bernoulli numbers. Can you see the Bernoulli numbers down here? These are just factorials. Z of u plus v, or z of u plus v plus 1 vanishes when m is odd. Notice the smallest value here is 2 or 3, so we don't have to bother about the first Bernoulli number. So it's equal to zeta of an even integer divided by pi to that even integer. So it's related to the absolute value of a Bernoulli number. So please, Jean, if you can manage to make pill and pal illuminate this problem, I will be very, very grateful. Okay. So, now, of course, what we actually did, to be honest, right, is exactly the opposite. What everyone does before they write a maths paper, but you never tell people what you did. You leave out all the human drama. You denature it. You take away your intelligence and your originality and the creativity and present dry, desiccated formulae like I've been doing down here. So what really happened? You know what really happened. It's what happens in your own work. You start at the end and you work back to the beginning. You never work the way your papers are written. So the real drama is that we started playing around with these numbers. And you see, I've been looking at 2 by 2 determinants, so I'd already had quadratic combinations of them. And so the obvious thing was to look at larger determinants, and you'll see that gave beautiful results. But then we said, maybe Legendre goes on forever. Even though we're beyond elliptic integrals and beyond modular forms, maybe there are quadratic relations. So we looked at the elements of these beautiful period matrices that give the L-series that I'll tell you down there, and we found that empirically we could take rational linear combinations of products of them and get rational numbers. And that's the amazing thing, right? That happens. Now, when any deep algebraic geometer like Deligne sees that and so on and so forth, they say there's an underlying motive, and there's a Betti cohomology and a Rham cohomology, and they're encoded by matrices. And there should be a rational relations between determinants of the period matrices and critical values of L-series. So down here we said to ourselves, look, we're touching something very deep. You know, Birch-Swinnerton Dyer conjecture has a quadratic form here just defined by the Néron-Tate height on an elliptic curve. This is much bigger, much more beautiful, and it goes on forever, even though my ability to calculate the rational numbers associated with the L-series. So we said these must be very special. And of course, we've got the elements of matrices, and we've got the matrices going with n, and then suddenly David Roberts said, oh dear, he said, I've seen 691 in one of these integers on the left-hand side. I said, that's the most beautiful number in the world. These Betti matrices are zeta valued. Underlying this is a pure motive, I am told, by Spencer Bloch and by Francis Brown, a pure motive. And the things that we're getting out of here only involve when you take out powers of pi. Remember, 2 pi I is equal to unity to every good mathematician. So when I take out these, I'm seeing the Bernoulli numbers. So how did we find this amazing construction of the Néron matrices? Well, it's obvious. We did everything backwards. We said we've guessed the Bernoulli matrices. Now we multiply by the inverse of P on the right and the transpose of the inverse, work out numerically these matrices, find what rational numbers they correspond to, and then do pattern recognition of this rational number. And this is a huge enterprise to go from this huge amount of rational data, you know, to find out that the A-B matrix element of the Rham thing is a polynomial times c to the n, summed over some c's. But then it's a polynomial in 2 variables. So we accumulated, this is detective work of an extraordinary high standard and very demanding. But at the end of the day, I can throw away the drama of it and just give the definitions. So we found out that these polynomials down here in the n and the number of Bessel functions were better written in terms of this h. And we found recursion relations like this. And then we empirically determined what these constants were by going up to 22 loop diagrams. And then we tried to find a generating function for them, and that took another week. So at the end of the day, what I've given you is just a mathematical theorem, right? Just the whole of the human story taken away from it, and it will probably appear like that on the journal. What a waste, what a shame. Try and talk about yourselves when you write your papers. Bring some humanity into your work. So now I want to tell you, in the 10 minutes remaining, the relations to L-series. And here, I've told you the name of the game, right? I know how to construct my L-series. So I'm starting off here with 8 Bessel functions. And here I've given a particular example. The critical strip runs from 0 to 6 at s equals 4. I get this sunrise diagram. This is a 6-loop sunrise diagram that will be one of the numbers in the 6-loop magnetic moment of the electron. But now I just define larger and larger determinants. So this stands for omega 123 means put omega 123 at the top left-hand corner, so that's a 24-loop sunrise diagram, and it's a 5 by 5 determinant, and all I do, it's got a power of t in here, all I do is the next element has t cubed, t to the 5th, t to the 7th, and then I go down changing 2 k-naughts into an I-naught. So the next thing going down here would be I-naught cubed times k-naught to the 21. And I then take the determinant of that matrix. This recipe is deep in the lore of motivic theory and works in hypergeometric context studied by Fritz Beukers and Fernando Rodriguez Viegas. But they've never been able to go to these depths, because this is just a determinant of Feynman integrals, right? And which I can evaluate. 25 by 25 determinant to 1,000 decimal digits may take me a few minutes. These are extremely refined objects, and all I know in the first instance is they come from local data at the Pines with Kloosterman sums. So I need 25 gigahertz years of work. That's not too bad if you think about it, because I've been at it for 6 months on 50 cores, to calculate all of that rational data in finite fields with Q less than 250,000. And then I know the data at the first 250,000 primes and the powers of those primes, primes up to 250,000, and because it's a modular form, at things which are the products of powers of primes, I take the products of the Fourier coefficients. But then I have to find out what happens at the bad primes, guess. And then I have to guess what the conductor is and what the gamma factors are for the prime at infinity and what the sign is. But this is a finite guess space, and you'll absolutely know when you've got the unique answer when the functional equation is satisfied. When the numerical test of the functional equation is satisfied, then you've got down there. So when you do all that work, the interesting thing is, what are these nations? Well, you see powers of primes that divide the conductor down here, but you start to see numbers which are like 691. So this is the 24-loop Feynman diagram, and it gives this number 1, 2, 5, 5, 8, 7. This is the telephone number of this like 691. Now, maybe sometime in the future of humankind, it will be proven that this is a rational number. I doubt whether it will take even longer to prove it's equal to that integer. You see, because these are deep conjectures by Collinia, that there is such a relationship in such a setting. But they're in situations where the algebraic geometers can't deal with this huge variety, and the modular forms database, which is completely useless beyond 8 Bessel functions, we'll have to wait 100 years before it illuminates what's happening in the upper half of some planes on some Calabi-Yau manifold. So now we're just at the level of 691. And then, of course, when you do this, the first few become difficult, but then it becomes wonderful, So here now I've got different, same number of Bessel functions increasing by 4, with different arguments, and that just corresponds to cutting a line in a Feynman diagram at the top left of the matrix, and I find these numbers. Now here is something that really does impress mathematicians. For 12, 16, and 20 Bessel functions, we have a vanishing central, we have an odd sign of the functional equation, so it's like Mordell-Weil curves with odd analytic rank, and so we have a central derivative. Remember, the modular weight is the number of integrations, which is the number of Bessel functions minus 2, so that's 10. So halfway between 0 and 10 is the center of the critical strip, and it vanishes, so I take the derivative. And now I have, more refined things that involve enlarged matrix elements, one step larger, which are enlarged to include at the bottom right-hand corner a divergent integral. It's kind of nice. You have something down here that would be something like a regulator if you're in the elliptic concepts, and to actually find the relationship between the central derivative and this idea of a regulator, I regulate a Feynman integral. And that's the origin of my final joke. So then it just goes on, right? I mean, it's just like picking fruit off a tree. You've worked very hard to do this. Here they are for when the number of Bessel functions is equal to 2 mod 4, and here they are when the number of Bessel functions are odd. This one down here, normally when I get to 40 digits and I find that it's equal to 53 plus or minus 1 part in 10 to the 40, I'm satisfied. Here, 20 gigahertz years of work is only enough to give me 14 digits. So when you consider I didn't know what powers of 2, 3, and 5, and 7 to put in down here, this is something that probably requires more skeptical evaluation, but I believe it will probably survive further testing. So, in my remaining 5 minutes, yes, is that correct? I get to tell you about the diamond lattice. In the course of doing this, we had to regulate an integral. Now, physicists know all sorts of ways of regulating integrals, but the most obvious one that I could have explained 350 years ago to Daniel Bernoulli, is how to regulate his Bessel moment that I get when the number of I naughts is equal to the number of k naughts. Remember, this blows up exponentially, this dies exponentially. So this combination has an asymptotic series which begins with 1. So if I have too many powers of t, I'm integrating a positive power of t up to infinity, which is not a good idea. So I want to define something which is a regulated version of that. As long as I precisely say how I regulate it, everyone knows it as a definition, so I just integrate by parts. And if j is how dangerous I am, at j equals 0, it's logarithmically divergent. At j equals 1, it's quadratically divergent in t. So I just integrate by parts, formally throwing away powers of t squared at t equals infinity, until I get to the really interesting case where I only have a logarithmic divergence, and then when I integrate by parts, I don't get a power of t, I don't change the power of t, I get a logarithm coming in. And formally, I've included here any constant. To show that this is an entirely arbitrary object, because it's been regulated, I've thrown in a constant. Now, everything is beautiful that I said if I take the constant for even moments where there are, which means b is odd and t and c here is even, where I take the constant to be Euler's constant plus log 8. And the origin of that is this discovery, that this particular integral, now here it's got this f of t, and here I've differentiated it with respect to 1 upon t squared, essentially. Differentiate with respect to 1 upon t squared. These are perfectly well-defined things, and I assert that those are rational numbers for all j, and that j equals 0, it vanishes. And I have a closed formula for those rational numbers. Now, where Marilyn Monroe comes in is this problem where, by the way, I have central derivatives for Lseries associated with even powers of t. Those don't come from Feynman diagrams, but those associated with twisted Kloosterman sums. And you get beautiful numbers for central derivatives of those, but by regulating things. Now, I've already shown you the regulation of the Feynman diagram, and the regulation for the Feynman diagram involved a strange thing that I found that I got good formulas if instead of using this arbitrary constant to be equal to gamma plus log 8, that for the, down here, this means an even number of I naughts, an even number of k naughts, and hence an odd power of t, and hence a Feynman integral. You take gamma plus log 4. And here's now a discovery which is more difficult to prove. Here I'm taking any number of derivatives of the square of I naught times k naught squared, which is now why I want to go back to Marilyn Monroe and tell you that not only are diamonds are a gal's best friend, but they're also a cal's best friend. That was the point of it. So I'm going to show you that a cal's best friends are diamonds because they give an example of resurgence in the simplest context that I can think of it. So I can explain the following problem to Daniel Bernoulli, and I can get Gauss, I'm sure, to prove my assertion in an afternoon. So what I'm going to tell you is that there are numbers defined by self-returning walks on a diamond lattice. That's just the lattice of carbon in 3 dimensions. And I tell you, you take 2 n steps. You can go backwards and forwards however you like, but you have to end up how many ways of doing it. And that combinatoric problem was solved by Cyril Dombe in 1960. And here's his formula for it. So this is the rather nice combinatoric formula. Right? This is the number of self-returning walks of length 2n on a diamond lattice. And these numbers resurge in a Taylor expansion and in an asymptotic expansion. So I assert that the 4th power of Daniel Bernoulli's I naught, he actually had a j naught, but that just corresponds to changing t squared to minus t squared. These diamond numbers, so this is the generating function for the diamond numbers. I had a little bit of difficulty proving that, but do you remember, Eric, at the Lseries Summer School? You gave me the bijection between self-returning walks and special types of words. So, but certainly Gauss could have done that in an afternoon. But here now is my final thing. It is my final slide down here. Try proving this. Right? The I naught squared and the k naught squared, this does down here, And here, where you see massively convergent double factorial squares, here you see something that I would like to call Gevrey 2, but it's not really, it's really Gevrey 1, because it's the square of n factorial multiplying t to the 2n. And I discovered this empirically. I invite you to try and prove it, but I discovered it empirically because I was evaluating such things, and I like to look at their prime factors, and I found that prime factor, and I already had in my list that it was a prime factor of this series from that. So this is a beautiful example of resurgence, and it sets, I hope, up the scenario for a wonderful talk you're going to hear from Michael Borinsky, where this is just the beginning of a connection between Taylor expansions and asymptotic series. Thank you for your attention.
Okay, thank you very much for this beautiful talk, and apologies for technical difficulties. We have time for one quick question or comment.
How crucial was it?
Sorry.
How crucial was it that the building blocks were I0, K0, not some other Bessel function?
Probably not crucial. Should I? I've got the microphone here. Because actually, as you know, in 4 dimensions, we have I1 and K1, yes? But the number theory is the same. So I think that the underlying, I'm looking at one particular very simplest thing, but the underlying algebraic geometry is such that you could have any integer powers of integer indices of I and K, and I would be able to show that that's a period. And so you could look at the algebraic geometry. I don't promise that, but I'm pretty convinced I could do it, because all I would have to do is to differentiate with respect to external momenta and internal masses, and when you start to differentiate Bessel functions, you increase their indices. So morally, I think it's the same universe.
Are there any more very pressing questions? Okay, so if not, then we can maybe continue the discussion over the coffee break, and there will be an announcement. But first, let's thank David again.
Thank you.